Hello. In this video, I will talk about a poster that presents updates to my undergraduate research. This version of the poster was presented at the 10th Cal Poly Pomona College of Science Symposium in May 2015. An earlier version of this poster was number 256.15, the 225th American Astronomical Society meeting in January of 2015. As we zoom in a bit, an important thing to notice is the co-authors. Dr. Shar was my mentor while I was at my internship at the SETI Institute, and Dr. Povich was my undergraduate project advisor. Drs. Jones, Egan, and Thielens helped write the software for these simulations. A quick pan down brings the methods and results into view. The goals are the same as before. The background is similar too, but is worth reviewing. A carbon star is a dying red giant with plenty of carbon materials from its core. As it dies, it loses most of its mass, throwing carbon dust into space. Most of the carbon dust in space comes from stars like this. There are different types of carbon dust that I keep track of using the hydrogen atom fraction, H/C. Few hydrogens in a molecule, aromatic, looks like the left of figure 1, where more hydrogens looks like the chain-like, aliphatic molecule on the right. When the rest of the poster talks about simulated and observed spectra, a spectral energy distribution is the overall shape of the spectrum, and features are specific peaks I am interested in. The software used for the simulations uses Monte Carlo methods to solve how the star's light travels through the dust. Dust type involves knowing specific, complex indices of refraction for the dust, and most importantly, this new model can use 2 grain types for the overall dust population. I varied H/C and grain size and wrote a script that plots the 3.3 micrometer comparisons in figure 4. Moving on to talk about the model results and conclusions, a good place to start is with the figures. In figure 2, I compare a simulated image at 11.8 micrometers to an observed image at 11.9 micrometers from Honey in 2003. The donut-like structure in the dust matches rather well. For figure 3, the overall spectral energy distribution also matches all right. The dust part of the SCD is a little bright, since it still passes over the feature at 21 micrometers, but there are improvements matching the star part and the middle of the distribution. Most interestingly, figure 4 shows some combinations of dust types and concentrations that I can match the emission features at 3.3 and 3.4 micrometers well. A through H in this figure correspond to an increasing hydrogen fraction for one of the dust types from 0.17 to 0.58. The details of these matches are specified in Table 1. Model parameters are on the right column, and the figure they relate to is listed on the left. First, for figure 4, part C, there are 2 usual grain sizes for my simulations, 1 micrometer large grains and 0.05 micrometer small grains. Here, there are 20% of the large grains with a hydrogen fraction of 0, and 80% of the small ones with a hydrogen fraction of 0.29. For figure 4, part D, and figures 2 and 3 mentioned before, there are 40% of the 0 hydrogen fraction and 60% of the 0.35 hydrogen fraction. For figure 4, part E, there is a 50-50 split of large and small grains, large ones having a hydrogen fraction of 0, and the small ones having a hydrogen fraction of 0.41. Figure 4 and Table 1 constrain the hydrogen fraction of small dust grains to 0.35 plus or minus 0.06, less than 0.29, and the model does not have any features in the 3 micrometer region. Greater than 0.41, and the features seen are too strong at 3.4 micrometers to match the observations. The model also provides helpful numbers for the distance to the star, about 4 kiloparsecs, and how much light is lost as it travels that distance, the interstellar extinction number in the results section. Future goals for this type of research would be to answer these sorts of questions about other carbon stars, refine this model to account for more kinds of dust, and more complicated dust grains.